Beautiful. All right, so let's kick off. I think we've already gone through this, so we can skip the slide for now. Cool. So in terms of the content and topics that we're going to go through today, we're going to start with just a basic introduction of what R is. We're going to also introduce R Studio, which is the interface that we're going to use to run our R code. We'll start with some basic arithmetic, which is like plus, minus, times, and divide. We'll learn about variable assignment, comparison, data types, vectors, functions, loops and conditionals, props and stats, and then we'll take a break, and then Jude will come in and finish off with data frames and visualizations. So how we're going to run, today is we'll go through each topic. I'll sort of give you guys an overview, and then we'll hop onto RStudio and actually look at the code and how exactly do you do the different commands under those different topics. Any questions so far? All good? All right. Cool. So introduction to R, just a brief introduction to R. R is a programming language, as you know. It's mainly used for statistical analysis or data manipulation. And the main, IDE or integrated development environment that we use to run R is called R Studio. And R Studio has two different formats, but the one that I guess we'll all use today is our Studio Desktop, which I assume that most of you guys, if not everyone, has already installed onto your computer. And that's what we're going to use to run our code today. And on the right-hand side, why should you learn R? So R is a very popular programming language. As you know, it's open source, which means it's constantly being upgraded. It's constantly being improved by developers who are constantly adding packages that are used for different purposes. So yeah, it's pretty versatile, it's flexible. It's also easy and straightforward to learn once you start to pick up the basic syntax, which we'll go through today. And last but not least, if you're interested to work in like data science, if you want to work in a company like Quantium, it's something you just have to pick up because everyone who works with data knows or understands how R works pretty much. So that's what R is and R Studio is. We're going to start off, before we hop into the actual R Studio interface, I thought I'll give you guys sort of a brief overview of how the interface works. So R Studio, as we will see later, is broken down into 4 different quadrants. So we'll start off with the top left-hand side. So the top left-hand side is called what is called a script. So script is where you can save all your R code. It's where, if you're working in a project team and if you want to share your code around with different people, that's where you will save your code. You'll save it in the script, and then you can send that script off to someone else. And the top right-hand side is called an environment. So an environment shows you all the data, all the variables, all the functions that you have defined in your workspace. So say, for example, if you declared if you stored a value into a variable, and that variable will show up in your environment, just to keep track of what you have in your existing working environment, pretty much. And at the bottom left, we have the console. So console is nothing more than just a quick sort of space for you to test out your code. It's where, you can write your code and you can run it and see what the output is. And last but not least, at the bottom right-hand side, it's plot. So I won't be going through plot. Jude will be taking that through the second half of this workshop when we look at data visualization. So that is where the graphs or the plots will show up at the bottom right-hand side of RStudio. Cool. And some RStudio basics. I won't spend too much time here, and I'll try and call out these commands as I go through the workshop today. But what I want to call, your attention to is what's useful is the third one here. So one code from script, control enter, which we'll look at later, and the next one is remove save variable using a function called remove. Yeah, I'll give you guys a couple of seconds. I won't spend too much time here. I'll just call them up when I use the function later on. And some more RStudio basics. Cool. All right, so beginning with the first topic, which is basic arithmetic and variable assignment. So first of all, we have our just our basic add, subtract, multiply, divide. So this is the symbol that you use in R, and this is very consistent across most of the programming languages. So plus, minus, times is where we will use the star symbol, and divide is just the backslash. Next, we have power. So power when you're raising something to a power something. There's actually two ways you can do it. One is using the first symbol, and then the next one is using the double star. And integer divide. So how integer divide is different from just normal divide is it'll only take the full integer. So say, for example, 7 divided by 3, that would be 2. And next we have modulo, which is taking the remainder after division. And last but not least, we have variable assignment. So variable assignment allows you to assign a value or a function to a particular variable. Cool. I think it makes more sense if we just go through the exercise, which is what we're going to do now. All right. Does everyone have the R file loaded or have opened up their R file / know how to do it? I guess I'll just show it. So say, for example, if I close this up now. So this is what you would have if you just open up RStudio as it is. And if you have already saved the file that I'm guessing most of you have, you just go to File, hit Open File, and you just hit on the R script that would send it out to everyone, and you will get this. Cool. All right. Any questions? Otherwise, I'll kickstart our first exercise. All right, no questions. Yeah, so there's two ways you can do it. So this R script is, so yeah, as I mentioned, this top left bit is what is called a script. So we've saved this entire file as a script. And so when you open it, it'll appear on the top left-hand side. And the way you would run the script is by doing Control-Enter. So if you just go at the start of the line of code, so line 4, and you just go Control-Enter, and R would run the output. And the output is at the bottom left-hand side. So 1 + 2 is 3. Another way you can do it is rather than running the script, you can actually do it from down here. So 1 + 2. This should give you the exact same result. Yeah, I'll give you guys a couple of seconds just to, I guess, play around and get used to it. So feel free to run this different commands. So 5.5 - 1, you can either run it from here, or if you want to try out running code from the console itself, you can also do that. So 3 × 2, it's 6. Just give you guys a couple of seconds to play around with that. All right, cool. We're going to move on to variable assignment. I think I've made a mistake when I was preparing the script. So variable assignment is actually at the bottom. So you have to scroll down a little bit past the comparison logical operators. So what variable assignment is, as I said, you're assigning a value to a variable. So here we're assigning 5 to the variable called A. So we do assignment in R via this arrow method. Or alternatively, you can do the equal sign. So here I'm assigning 5 to the variable called A. And when I do that, as we can see here in our environment, we can see that 5 has been assigned to A. We can see that the value A, the variable A takes the value of 5. And so now if I want to see what A is, I can just do A, and R will tell me that A takes the value of 5. Cool. What we can do next is we can update A to something else. So say, for example, if I change my mind, I want to update 5, I want to update A to something else. I can do A equals to A plus 2. So what this means is A, which was originally a 5, I want to add 2 to it, and I want to update the original A. So if I run A now, A should take the value of 7, which is 5 plus 2. And then, as we can see here in the environment, it's R is updated the value for A as well. Cool. And next we have just some practice to around variable assignment. So here I have semicolon on all the A, B, C, D's, and E's. So what semicolon does is rather than doing each letter individually, so like B equals to 4, C equals to -3. The semicolon allows you to do everything in just one line. So I can just do D equals to 600, semicolon, E equals to 10. So here I have all my variables assigned here. Cool. So now I guess just a tiny exercise. What do you think the answer for this one is going to be? Someone just want to shout out before we uncomment and have a look at the answer. Or you can cheat and just run it and tell me. Doesn't really matter. What do you think the answer is going to be? Any volunteers?
I think in the chat there are a few people saying 100.
100, yeah. Oh, I can't see the chat. That's the thing. Can I? Oh, I can. I'll just put it over here. Nice. Yeah. So it is 100. And the way you uncomment a code is just by, if you just delete. So just go to the script, just delete, and then you can run. So it is 100. Beautiful. So now I guess I want to demonstrate before we hop on to a different topic to how to clear your environment. Actually, first of all, let's clear the console. So this is what we call a console. So the way we clear a console is you can either do this, so you can press on this broom looking icon here, or alternatively, you can do Control L, and that will clear the console. And the way we will clear an environment, so the environment is the top right quadrant. The way we'll clear environment is by remove, so a function called remove. And you can pass in whichever variable you want to remove. So say, for example, if I want to remove the variable A, I'll just pass in A. And as you can see from the environment, A is gone because we've removed it. An alternative way you can do it, if you want to just clear everything and start fresh, you can do remove list equals ls. And this should clear everything in your working environment. So now my environment is empty. Beautiful. All right. Well, I'll pull up the slides again. We'll hop on to our next topic. So our next topic is called comparison and logical, sorry about that. Comparison and logical operators. So comparison operators allows you to compare a pair of values. So is 1 greater than 2, and then it will return either a true or false statement. And here we have 1, 2, 3. We have 6 different commands we can use. So the first one is equal. So note the difference between the double equal sign and the single equal sign that we looked at in our previous topic, which is for assignment. Double equal sign is for comparison. So yeah, so it's important to note the difference. So this double equal sign will return either true or false. A single equal sign is for you to assign a value to a variable. So those two things are different. Next, we have not equal to. So this is pretty consistent across all programming languages. So the way you would do not equal to is you add an exclamation mark before an equal sign, and this will allow you to check if something is not equal to something. Greater than, less than, greater than or equal to, less than or equal to. Pretty straightforward. And next, we have logical operators, which is different from comparison operators. Logical operators allow you to combine different true and false statements together. So if you have two statements that you want to check, you can use either one of these to combine those statements together. So if you want an and to return a true, both if you have two statements, both have to be true, or both have to be true or both have to be false to return a false. If you use an or, just one of the statements have to be either true or false. This will make more sense as we have a look at the exercise. But yeah, so that's pretty much it on comparison and logical operators. We'll go back to RStudio to have a look at the exercise for comparison logical operators. So here, same thing. 5 greater than 3. So this should return a true because 5 is greater than 3. So if I run this, the output is true. The next one, -2 less than or equal to 5, which is also true. And next we have 1 plus 1 not equal to 3. So does anyone know what the output of this is going to be? Yep, it's going to be true because 1 plus 1 is 2 and 2 is not equal to 3. So this will return a true. And here is where we'll have the logical operators. So here we have the first line 23, we're using the AND symbol. So for AND, if I want something to be true, both of them have to be true. If I want AND to return a false, both of them have to return a false. So let's have a look. So 1 greater than 3. So this is false. 4 greater than 2. This is true. So what do you think this one is going to return? Yep, it's going to return a false because the first statement is a false. Yep. And what about the second one? So for the second one, we're using an OR instead of an AND. Yep, beautiful. It's going to return a true because we have one of them to be true. And just to, I guess, show you guys if that's indeed the case. So if I change the 1 to like a 5, for example, so 5 is greater than 3. So this is true. 4 greater than 2 is also true. So this should return true. Cool. All right, let's get back to the slide. All right, so next topic we have is called data types. So data type is what is called an attribute. So data type informs or tells the computer, tells R at least, how to interpret a certain value. So there are 3 main categories or 3 main data types. The first one is called numeric, which represents all the numbers. So the numbers could be either integer, it could be a floating point number. I just categorize everything as under numeric. So all the numbers will get data type of numeric. Next, we have character. So character is a string. So if you are, so if you're familiar with programming, a string, usually how you identify a string is by the quotation, the open inverted symbol. I don't know what you call it. So this is how you would, I guess, tell if it's a string or not. So hello world, this is a string. And although this one, 808, this might look like a number. You might be tempted to think that it's a numeric, but this is actually a string. And the way we tell it is because of the 2 symbols we have at the front and at the back of 808. And last but not least, the third data type is called a logical or Boolean, which is what we saw exactly just then with the comparison operator. So this would be your true and false statements. So this would take the data type of a logical, or sometimes called a Boolean value. Cool. So those are the 3 data types that you need to know, I guess, in R. Let's now hop on to R Studio and run some lines of code. Cool. And so yeah, so the function that allows us to check the data type of a variable is called class. So the class function will take a variable or a number. You just need to pass it in, and then the class function will return the data type for that particular variable or value. So let me just go ahead and clear the console first. So if I run class pi, pi is a numeric. So if you don't know what pi is, you can actually run this. So pi is already inbuilt into R itself, so you don't have to declare it or anything. So if you want to have a look at what pi is, you just do pi, and you can see pi is 3.141593. And so therefore this one is a numeric. Same thing goes with 808. So this would be a numeric as well. And hello world, this one would be a character because this is a string. And as I said early on, this 808 is different from this 808, and you can tell by the color as well. So our colors their strings or characters as green, and their numbers as blue. So if I run this, this should give me a character rather than a numeric. Yep. So as you can see, this is different from this. Yep. And the last one is what is called a logical. So if we check the class for true, there should be a logical data type. And the same thing goes for this. So 2 less than 5. So this will return a logical statement, i.e. a true or false. So this should be a logical data type as well. Beautiful. All right. What do you think will happen if we run this. So if I uncomment this and run this, what do you think is going to happen? Yep, it's going to return an error. And the reason is because 808 is not a numeric. 808 is actually a string, and we can't do arithmetic with strings. So this will actually return an error. So if we try this, so this is the error. Non-numeric argument to binary operator. Cool. So if we want to do this, there's, well, two ways you can do it. Either you just remove the symbols and just do 808 by itself, or there's another function you can use called asNumeric, which will turn a number into numeric form. So if I pass in 808 in string form into asNumeric function, this will turn the 808 in string to number. And once we do this, we can perform any addition, multiplication, anything like that. So if I run this, there should be no issues. Yeah. So that's one of the key, I guess, importance, or the key takeaway from this particular exercise. It's that the reason why we make a distinction between all the different data types is because different data types can allow different sort of transformations. So you can't add, it makes sense, like, because you can't do addition to a string, because string is just like a sentence, and R is smart enough to capture this. So if you do this, this will actually return an error. And if you want to do addition, everything, all your data should be in numeric. Cool. We're going to move on now to our next topic. Any questions so far? Am I going too quickly? Am I going too slow? I think it's all good. All right, we're going to jump. We continue. So next one is called vectors. Our next topic. So vector is a data structure. So data structure is how R stores your data. Vector is an example of data structure, and Jude will introduce you guys to a different data structure later on, which is called a data frame. But vector is one of the many examples of a data structure, which is how data is stored. So vector is one-dimensional, which means it's just one single line. And it's an ordered collection of data of the same data type. So this is important. So vectors can only store data that are of the same data type. So say, for example, if you declare a vector that's going to store numeric, you can't have that vector storing something else. So it has to be all numbers. Same thing goes for strings. If you want to have a vector that stores only strings, it should be exclusively strings. If you want to have a vector that stores logical, it should be all logical. So it should all be the same data type. We can add, alter elements in any given vector. So element is, I guess, a programming language. Not language, it's like a thing we call it. So element is the thing inside of a vector. So if a vector has like 3 elements, it means that's like 3, I guess, data points in it. That's what we call an element. And there are built-in functions in R specifically for the purpose for creating numerical vectors. So which we'll look at as we run through our exercise. Cool. Want my R again? Cool. Yeah, so the way we'll create a vector is using the C, what do you call it? Is this I don't think it's a function. So this is just how we create or declare a vector. So it's a C, and then whatever value you want to put inside that particular vector. So here I have a vector that contains strings, and it has 3 elements. So this is my first element, this is my second element, and this is my third element. So this vector is called player names. So you can also assign a vector to a variable. So if I run this, we can see in the environment I now have a player names vector defined, and this vector contains 3 elements. So it's of the data type character, and it has 3 elements, so 1 to 3. So if I print player names, this should show me all the elements in that particular vector. So Michael Jordan, Michael Phelps, Michael Jackson. And here I have another vector. So this one is numeric. So notice how this vector only stores numbers and nothing else. So if I run this, and if I want to have a look at the vector that I've defined, this is my point scored vector, which has 3 numbers. Cool. All right, so another pop quiz. What do you think the following will return? So let me just uncomment this. So a shortcut for you to uncomment a chunk of code is Control-Shift-C. If you're on Windows, you just highlight the chunk of code that you want to comment/uncomment. Just do Control-Shift-C rather than going line by line. But yeah, so if I declare this vector called invalid vector, which has 3 elements, and if I check the type of, yes, I should introduce what type of. So type of will return the data type of that vector, which is similar to the class function that we looked at. So type of is for vector. So this will return the data type for that vector. So does anyone know what type of it's going to return for this particular vector? Characters, yep. Cool. Yep, so it is indeed a character. And so the reason is because, as I said at the beginning of when we introduce vectors, vectors has to be all of the same data type. So here, this vector contains 3 different data types. The first one is numeric, the next one is logical, and this last one is a string. So this doesn't actually work. So what R is going to do if you actually define this, it'll just turn everything into a string, and therefore when you run the type of function, it'll just return characters. So if you have a look at the invalid vector, you can see that all the numbers, both the numbers and the logical have been turned into characters or strings. So R has added the quotation marks around it. Yep, cool. And next, we're going to move on to accessing and adding elements in a vector. So the way you would access an element is using a square bracket. And R has starting index of 1. Like if any of you have coded in Python before or any other programming languages, some start at the index of 0, but R starts at the index of 1, which means if I want to have a look at the first vector of the player names, the first element of the player names vector, this is how I would just pass in the number 1. And so this should return the first element of the player names vector, which is Michael Jordan. Yep. And yeah, and the same thing goes for point scored. So this will return the 3rd element of the point scored vector. So our point scored vector is this. So this should return, excuse me, the number 13. Cool. And to add an element to a vector, we can do this. So here I am declaring a 4th element in the player's name vector. So right now my player names only has 3 elements. If I want to add a fourth element, I can do player names open square bracket 4 close square bracket, and then I can assign another name to it. So if I add this, we can see here in our environment, our player names now has 4 elements, and yeah, 4 different names. If you want to have a look at the console itself, what those 4 names are, you can just type it out. So now we have an additional Michael in the vector. Cool. Any questions so far? All right, we're going to introduce a few more functions. So this one, so in allows you to check if an element is in a vector. So this will return, this is a statement that will return either true or false. So this is essentially checking if Michael Phelps is in the player names vector, which it is. It's the second element. So this should return a true. And if you want the specific placement or the specific index of that element in that vector, you can use the match function. So what match is saying is return to me the index number of Michael Phelps in the player names vector. So this should return 2 because Michael Phelps is the second element of that vector. Cool. Yep, type of, which I think we've already discussed early on. So type of will return the data type of that vector. So player names is a string and it's also a character, so we'll return a character. Type of for point score, because point scores are just numbers. So this will return numeric or a double. Yep. So another function, useful function that you should know is called length. So length will return the number of elements in a vector. So number of elements for player names would be 4 because we have 4 elements. These 4 elements here. Sorry about that. And the length for point scored is 3 because we have 3 numbers in this vector. Cool. We're going to move on to creating vectors. What we just looked at are just like accessing, or if we're adding just one single element. We're going to now look at how to create numerical vectors, and the different functions that you can use that are already built into R that allows you to create vectors. The first one is not really a function, it's just like a built-in feature that R has. So 1 semicolon 10. So this will allow you to print from 1 all the way up to 10. So if I run this, so this creates a vector of 10 elements starting from 1 all the way up to 10. And you can also do with decimal numbers as well, floating point numbers. So if I do 0.5 semicolon 5, this is going to create a vector from 0.5 to 4.5. So the reason why it's only until 4.5 and not 5 is because R looks at the first number that you use to define the vector, especially when you're using the semicolon. It will just look at the first number. So say, for example, here you're using 0.5. It will just recreate the vector that's 0.5 by increment. So it's going to go 0.5, it's going to go 1 time. So 0.5, 1.5, 2.5. And it's going to stop at 4.5 and it won't go beyond 5 because that's where your ending limit is going to be. Does that make sense? Cool. So yeah, so by default, when you're using the semicolon, you just R will just either increase or decrease by 1. That's just the nature of the semicolon. So if I do 6 semicolon negative 2.4, so this time we're going in the negative directions, we're actually decreasing. So if I run this, R will go 6, 5, 4, 3, 2, 1, 0, -1, -3. And we won't go till -3 because we've set the ending limit at -2.4. Cool. So if we want something more robust, rather than just having it to increase or decrease by increments of 1, R has a function called SEQ. I think it's short for sequence, if I'm not mistaken. So sequence allows you to create a vector that's more, I guess, in a more flexible way, rather than just having to increase or decrease rather than just having to increase or decrease by 1. So sequence works, 3 main arguments that you can know is the starting point. So 1 is my starting point, 10 is the ending point. By just tells R what's the increment that you want to go by. So if I run this line of code, what's the purpose of the 0.4? So yeah, so the reason why I have these 2 lines of code is to, I guess, to show you guys that R will only stop at 4.5 or -2. It won't go past 5, because this is the ending, this is the limit that you've set on that particular vector. So it just decrease. So for example, this 0.5 example will just increase until 4.5. Because the next, if R just kept going, it will go to 5.5, right? But the limit, but the ending point you've set here is actually 5. Yeah. Cool. All right. We're going to keep going. So sequence. So sequence is you have to define a starting point, an ending point, and the increment. So if I run this, this is going to create a vector that starts from 1. It's going to go to 1.5, to 2.5, all the way up to 10. So this, the sequence function is more flexible, as you can see, because you can actually explicitly tell R what the increment is going to be, unlike if we just use the semicolon. So here I've specified a 0.5 increase from the starting point of 1 to all the way to ending point of 10. Another argument you can use is called length out. So length out tells the sequence function how many elements you want to create in that particular vector. So here the starting point is 0. We're starting from 0. We're going to 1, and I want you to split the vector into 4 equal parts. So if I run this, R is going to create a vector of 4 elements. It's going to start from 0, which is our starting point. It's going to end at 1, and R is smart enough to divide this equally into 4 equal pieces. So 0.33, which is 1 over 3, 2 over 3, and 3 over 3, which is 1. Cool. Any questions? I think I'll just wrap up. We'll have so the last function that you need to know is called repeat, or REP is short form. So repeat, as the name suggests, is just how many times you want to repeat a certain value or a certain vector. So here I want to repeat the value pi 3 times. So I'll just need to pass in pi, and then the next argument is how many times I want to repeat that particular value. So here I have 3 values for pi, and you can also apply this in a vector as well. So I want to repeat this vector twice. So if I run this, the output is 1, 2, 3, 1, 2, 3. Beautiful. All right. I think I've talked enough. Do we have time functions? Yeah, I think we'll have time. Let's just do a quick vector exercise. I'll give you guys some time to work through these questions. We'll just do 2 minutes, and then we'll continue with our next topic. All right, let's carry on, because you guys will get a copy of the solution after this workshop. There should be a simple vector exercise just to get you guys familiar with what vector is. For interest of time, let's move on to our next topic called functions. Yeah, so function is really important when you are coding, when you're programming. Function allows you to organize your code or a piece of analysis that you're doing. Function is a way for you to break down a big problem down to smaller individual components, so that it is easier for you to go back if you want to review your code. You can go back and sort of review a certain part of the problem that you're trying to solve, rather than having to sort of browse through the entire piece of code that you've written. Function will allow you to do that. So function is just like a small, tiny component that you can sort of break your problem down into. So function performs a certain task that can be readily reused. So function usually performs a very specific task. So a smart way to write a function is if you say, for example, if you're solving a problem that involves many parts, you want to break those parts into smaller pieces and have a function represent each piece, and the function would sort of do a very specific task that you can then reuse in later down the line. So a function involves a simple three-step process. So it's input. So a function will take an input and you'll process the input, and then it will spit out the output. So it's very simple three-step process. You give a function something, the function will then process that something, and then it will output a certain thing that you want that function to do, essentially. And yeah, so now we're going to look at some built-in functions, which is functions that already exist in R. You don't have to define yourself. And then we're going to move on to looking at how we can construct our own functions. Cool. So these are all built-in functions. So absolute, we have square root, round, log, exponential, and sine. So app is just absolute value, so it'll turn a negative into positive. Square root of 49 is 7. Round is just rounding the number to the decimal places. So here I'm rounding the number pi to 2 decimal places, so 3.14. Log is just log, so log base 2 is 3. Exponential and sine. So yeah, so these functions are already built into R, so you don't have to recreate, you don't have to define yourself. These are already built in to R at your convenience. Cool. Now we're going to move on to actually writing our own function. So how do you write a function in R? So the way you would write a function is using, unsurprisingly, a function using the function command, and you have to specify the input that your function is going to take. And then you're going to use this open squiggly, I guess, parentheses in the closing. And this is where you would define your transformation. And then at the end of the function, you want to return the output. So that's the three-step process is pretty apparent here. So we have our input, and this is our process, our transformation. And then the function is going to return an output. And specifically what this function does is it'll take the input. It will take the input multiplied by 10, and I'm saving the result into a variable called output, and then I want to return the output. So taking the input, multiplied by 10, return the output. So this function essentially is just multiplying a number by 10. So if I apply this function, if I pass in the number of 1, it should return, sorry, I should define my function first. Yeah, so my function is already defined. So as you can see here in our environment, my function is called my first function. And so now if I pass in the value of 1, the function will return the value of 0. Because 1 times 10 is 10. And if I pass in 10, this function is going to return 100. Cool. All right, let's look at something more complicated. So this function only takes in 1 input. You can have the function taking as many inputs as you want, I think. I don't think there's any limits to my knowledge. So this function is called Euclidean distance. So this function will calculate the Euclidean distance between 2 points. So here I have 4 inputs into this function. So we have the first x coordinate, the first y coordinate, the second x coordinate, and the second y coordinate. And notice here I've default I've set the default for x2 and y2 to be 0. You can actually do this. So what this means is if the user of this function doesn't specify anything for x2 and y2, R will just assume that it's 0. What do you mean by return? So return is just a function. It's just a very it's just a syntax in when you're doing function. So return will just how do you explain? So is what you want your function to output. So here in the first example that we looked at, return will return the result after multiplying by 10. Yeah, so the function will return the output in that way. That makes sense. Yeah, so anyway, so yeah, so here I've default x2 and y2 to be 0. And this is the transformation. I know this looks like complicated, but this is nothing more than just the Euclidean distance formula. So you find the difference between the x coordinates, you take the square, plus you take the difference between the y coordinates and square, and then you want to square root everything. That's pretty much what the function is doing. And then I want to return whatever the output is going to be. Yep. So once I define this function, I can see that my function's already been defined in my environment. And so now I can go ahead and use my function. So here I have, I want to pass in x1 is equal to 5 and y1 is equal to 0 as my input. And because I didn't specify anything for x2 and y2, the function will just assume that I want output to be 0. So if I run this, we can see that the distance between 5, 0 and the origin is 5. Yep. Any questions? Otherwise, we're going to move on. I think we're going to skip exercise 1 for now, and then we can just go through exercise. I think we'll just go through exercise 2. Yep. So exercise 2 is this. Maybe have a quick read, and then we can go through it together.
Jason, I think there's one question in the chat from Sue.
What's the difference between return and print? So ideally, when you're writing functions, you want the function to return something, because print is what you use to print something on the console, whereas you want the function to actually return a value when you call that specific function. So usually, when you're using a function, try to use return. Print usually at work, if your print is usually like if we just like sneak in print at if the function is pretty like complicated, we'll just add like a print in the middle just to keep track of what the function is doing. But if you intend on that function to perform something, it's best that you use a return. So that when you need it in the future, you can just call the function.
I think what's confusing, Sue, is because if you don't assign the output of a function to the variable, it just dumps to the console. So if you were to do something like x equals my first function 10, it wouldn't print to the console. It'd create a value, like a variable called x, and assign the value there. If there's nothing to assign the output to, it just prints to the console.
Yeah. Does that make sense? Nice.
Great.
Cool. All right. I hope you guys had a chance to go read through exercise 2. We're just going to walk through it now. So essentially, so a group of children has collected some candies, and they want to evenly split the candies up and smash whatever is remaining. So we're going to create a function that does that. Cool. We're going to create a function called Candy Crush. So this is the name of the function. We're going to use the equal sign, or you can use the arrow symbol. It doesn't really matter. So we're going to use we're going to call on function, And this function is going to take in two things, right? Because from the question, we can see that the function needs to take in the total number of candies. That's our first input. And the function also needs the number of children. Cool. So now we're going to define those two arguments within the function itself. So the first one would be the, let's call it number of candies. And the next one is number of children. Cool. So these two are my inputs that the function will take. And then I want to do the open squiggly thing, parentheses. And this function is going to return. Does anyone know which arithmetic or operation that we need to use? Which symbol do we need to use? Plus, divide, modulo. Beautiful. Yep. So we're going to use the modulo. So number of candies. So modulo is the double percentage sign. And we're going to modulo by number of children. So what this means is if number of candies is 7, for example, and the number of children is 3, the remainder after division is going to be 1, because 7 divided by 3 is 2, remainder 1. And modulo will return the remainder after division. Yeah, the output is going to be 1 in that scenario. So 7 divided by 3 is 2, remainder 1. The modulo will return 1, and that's what we want. So if I go ahead and define my function and say, for example, I want to pass in, let's just use 7 and 3 because we just talked about it. So 7 candies and 3 children. So if I've done my function correctly, this should return a 1, which is what the function returns. Yeah, I hope that makes sense. So I guess just to summarize, function takes in inputs. The function will then compute something, do a transformation or some sort of arithmetic to it, and then the function will return an output. So input, process, output. Very simple. Cool. Let's move on to the next topic called loops and conditionals. So if you've done programming before, loops is another main, I guess, concept that you need to know. So loop is just, as the name suggests, will repeatedly run a piece of code. If you want a piece of code to repeat a certain number of times, or if you want the code to keep running until a condition has been met, loop is the way you do it. And there are two types of loops. The first type is called a for loop, and another one is called a while loop. Another thing that you need to, I guess, know when you're using loops is what's called conditionals. So if-else statement. So if-else statement will allow you to set a condition that will enable your loop to run and to know when exactly to stop. If that's when if-else statement comes in. We'll look at some examples just to make things more concrete. So if we go to the loops and conditional section. So here I have a simple function. And we know this is a function because it has a function, it has an input, and then and this is what the function does. All right, let's look at what this function is doing. So this function takes in one input and it checks if that input is true. If it is true, then print bring an umbrella. If else, which means if it's not true, then print no need for an umbrella. So if I run this function, and so if I do equals to true, which print statement do you think the function is going to print? The first one or the second one? Any responses? Let's just run it. Yeah, so it's going to be the first one because the statement is true. And because this condition holds true, I will just run this particular statement. So if I change this to a false, it should print this one. Yeah, so that's just a simple, I guess, introduction to what if statement is doing. So if statement allows you to set a condition. If that condition is satisfied, what do you want R to do? If else, else, if that condition fails, what do you want R to do? Cool. So now we're going to look at for loop. So for loop is our first kind of loop. For loop so the key, I guess, defining feature about for loop is you need to, I guess, define a starting point and an ending point. So here we're looping through a vector from 1 to 10. So for I, so this is how you do for loop. For and then open parentheses, I guess a variable in, and then a vector. So here we're looping through a vector from 1 to 10, and for each element we're taking the square of that particular element. So if I run this, it should return 1, 4, 9, 16, 25, and so on. So what this is doing behind the scenes is R will start from 1. So 1 square is just 1. And then it will go through, go to the next element, which is 2. So 2 square is 4, followed by 3. 3 square is 9, all the way down to 10. 10 square is 100. So that's the reason why you have this 10 outputs here. Cool. Yeah, so let's replicate the sum function. So there's a built-in function in R called sum. So sum will just basically sum up all the numbers in that you pass in. So sum from 1 to 4. So 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. So that's what the sum function does. So if you want to recreate our own sum function, this is how we do it. So we need to define a function. The function is going to take in a vector and this open squiggly thing, which is just how you define a function. And it's also how you define a for loop. So notice how we use these curly brackets. Yeah. So this function will take in a vector. And here I've initialized a variable to 0. So initialize just means I'm assigning a value to something, just to kickstart our function. So what this function will do is it will loop through all the elements in the vector, and then it will add the number to the variable called result. And then, yeah, it'll just loop through all the elements in that vector, and then it'll keep updating the result variable. And once it finishes looping through the entire vector, and then you'll just return whatever the result is going to be. Does this make sense? Cool. So if I define this function, and if I run my function on 1 to 4, so this is a vector of 1 to 4, which should return 10, which is exactly the same as this. Cool. All right, the next loop that we'll learn is called a while loop. So this is slightly different from a for loop. So for loop, we have to set a specific, I guess, vector or a starting point, ending point for the loop to go through. While loop is, for while loop, you have to set a condition. So rather than setting a vector or anything, while loop takes in a condition where you'll keep looping through until that condition has been met. So here I've initialized j to be 1. So j takes the value of 1. And what this while loop is doing is, as long as j is less than or equal to 10, I want you to print j, and then I want you to update j to j plus 1. So if I run these two lines, I get the output of 1, 2, 3, all the way down to 10. So what this is doing is, j is initially 1, so the while loop will check if j is less than or equal to 10, which it is because it's 1, print 1, and then update 1 to 1 plus 1, which is 2, and then it'll start back at the beginning of that while loop again, and check is 2 less than or equal to 10. It is. So print 2, 2 plus 1 is equal to 3, and go all the way until number 10, which is where the while loop will stop. So once it reaches 11, 11 is greater than 10, and so it will just print. It won't print because it fails the condition for that while loop. Cool. All right. I think we're a bit short of time, so I'll speed up a little bit. So here's a challenge question for you guys to take home and try yourself. You'll get the solution, as I said. This is pretty challenging, so no hard feelings if you don't get it the first try. For now, I want to, I guess, wrap up the topic and then give you guys hopefully a small break before Joe continues with the second half. So the last, I guess, topic that I want to go through with you guys is called probability and statistics. So as I mentioned at the very beginning of this workshop, R is mainly built for statistical analysis. So it's really meant for probability, it's meant for statistics. And R has a lot of built-in functions as well that enables you to calculate summary statistics. So stuff like median, what's the average, what the minimum value is, what the quantiles are. You can also do probability distributions. If any of you guys study like actuarial studies, we do a lot with like probability distributions. So like binomial, the normal distribution, Poisson, those sort of things. Those things are already like R has a lot of really useful functions for probability distributions. And the last, I guess, topic I'll go through under props and stats would be hypothesis testing. All right, cool. Let's switch back to RStudio. So you can just run this yourself. So here this is just a vector called X, which contains 10 elements, and these are the functions for you to, I guess, play around with. So mean is the average, median is just the median, variance, standard deviation, quantile, maximum, min. Summary, I guess summary is a pretty useful function. We'll just return most of all the summary statistics. So starting from the minimum, the first quartile, median, mean, third quartile, as well as the maximum value. So yeah, summary is pretty convenient. It's just a quick, I guess, snapshot of what your vector is and what the data is. Cool. We're going to now look at some probability distributions. So yeah, don't I guess worry I guess it's pretty important if you study like actuarial, if you do a lot with probability distributions, this one would be quite handy. But if you don't worry about it too much, I guess. So you can do help distributions. So help is a function in R that will show you all the documentation. So if I run help distributions, this thing will show up at the right bottom corner. So you can have a read through if you want to check what a function does, for example. If I want to check what sum does, I can use the help function to do it. So sum is just the sum of all the values present in the argument. So that's what the help function does. So if I go back to help distributions, these are all the distributions that are available in R. So you can have a read through this, I guess, yourself. You have normal distributions, all the different distributions in there. So I guess what I want to call out for this particular section is the different things that you can do. The first one is called, you can calculate the density. So here I'm calculating the density function for a binomial distribution. I guess it's worth just highlighting. So this, this is the number of, so 2 is the number of success, 3 is the number of trials, and this is the probability of success. So if I run this should return the probability. And this latter part of the code here is just to show you that you can actually, this corresponds to the PMF, so the probability, the permutation, what's it called? Probability mass function. This is the probability mass function for a binomial distribution, and it corresponds exactly to if you run D binomial. And this is the density for a Poisson. And what you can also do cumulative. So cumulative will return the probability, the cumulative probability. So here I'm doing the cumulative probability for a normal distribution, for a standard normal distribution, because we have a mean of 0 and a standard deviation of 1. And I want the probability, the cumulative probability starting from 0, which is just 0.5, which is because we're just taking the midway mark of the standard normal distribution. You can also do quantile. So quantile, you need to pass in the probability, and it will return the exact value for that distribution. So here I'm applying the quantile function to the chi-square distribution with the degrees of freedom of 2. And the last thing you can do is what is called a random variate generation. So here I'm creating 10,000 samples of the exponential function that has a parameter of 2. So if I have a look at what random exp is, it's just 10,000 values of 10,000 different values that come from the exponential function with the rate of 2. Yeah, and I guess it's worth pointing out the way you do like density is adding a d in front of the name of the probability distribution. Cumulative is p, quantile is q, random generation is r. Yeah, so these are the 4 main things you can do with probability distribution. So d, p, q, and r. All right, so the last, I guess, section under this topic, we'll just do a quick hypothesis testing. So here we're doing a t-test. So here I have a vector called rain, which contains all the rain amount. And you want to check if the rainfall has increased from its long-term value of 22. And then we need a t-test for this. So I'm passing in the vector into my t-test function. And I want to check if it's greater than 22 at a 95% confidence interval. So as you can see here, this is the output. So it will show you the p-value. You can see the test statistics. You can see the degrees of freedom, the confidence interval. So yeah, so these are pretty like statsy kind of stuff. If you want just like specific output from this test, if you don't want to look at the whole thing, you can assign this test to a variable. So here I'm assigning this test to a variable called rain test. And if I want a specific output, if I don't want the whole thing, if I just want to have a look at the test statistic, I can use the dollar symbol. So a dollar symbol in R means you want to extract something out of a variable or a data frame. R uses a dollar symbol. So this tells R, I want to select, show me only the test statistic of the t-test. So this will just show you the test statistic, 2.57, which is exactly the same as this. So this is just the small tiny component of this whole output. And the same thing, if I just want to have a look at the p-value, I can do dollar symbol p-value. So this is going to show me the p-value. So if I'm doing this by 95% confidence interval, if you know your stats, this would tell me to reject the null hypothesis. And the last example I want to show you is the confidence interval. So this will just show you the confidence interval. So 23 to infinity. Cool. So I think that wraps my part. I'm going to hand it over to Jude now to continue.
Cool. So I'm going to be talking first about data frames. So they are a very important data structure. Basically, everything you want to do will be done in them. They are what feeds into all the predictive modeling algorithms in R, as well as great for drawing graphs and all sorts of stuff. So it'll look like a table. I'm supposed to have a diagram there. Never mind. It'll look like a table when you look at it in R. So for example, so R, just by the way, has a number of data sets saved in it that you can use just to sort of practice getting your code right. They're all pretty small. This is a famous data set to do with, they measured various parts of an iris, of 50 different irises for different species, and determined that like there's very distinct differences in the sort of flower shape and size based on the species. So this will all be built into your version of R as well. So we'll be using a couple of data frames. MTXRs is what we're using first. So this is got to do with various different cars by different manufacturers. MPG is like miles per gallon of gas. There's a bunch of metrics about the structure of the engine, like the number of cylinders, the displacement of something, I don't know. but we'll just be using this as an example. But you can see that we have a number of different columns and a number of different rows of the data frame. So the rows, if you can look at these two examples, these rows have names, these rows do not. And so depending on how you set up your data and how you want to access it, you may want to assign row names or not. Cool. So they are stored internally as a list of vectors of equal length. So each vector is one of the columns of that table. And so where this comes into it, and something that's worth saying, I think, about R in general, is some of the R error messages are very difficult to interpret. And if you do something wrong, if you're trying to do something to a data frame and you get a weird error message that says, you know, it gives you like a length and it says that the length is not what it's supposed to be, it might be that you're trying to run it over the columns when you need to be running the function over the rows or vice versa. So that's just something worth keeping in mind. But anyway, it's stored as these vectors, but when you look at it, it looks like this nice, neat table. I'm supposed to have a lot more slides than this. Okay, let's just go through this data. Okay, so there are two ways to make a data frame. You can make it purely from scratch. So Jason talked about vectors earlier. So if we make a vector of strings, which is based on these names, so Jude, Jason, John, we make a vector of integers. And you can see these are all storing to my environment, and a vector of department. We can then make a data frame by using the data frame function, and we just feed in these three vectors, and that data goes in. So the values of the vector go in as the observations, and the column names come from the names of the vectors. So that's a very easy way to make a small table. You wouldn't want to make it something huge. When you're doing real data analysis, probably you're going to be pulling in data from a CSV. CSV being a comma separated values file. When you double click it on your computer, it'll probably open in Excel, but basically it's just saved as rows with these values separated by commas. We use them a lot. At Quantium, they're good ways to store big data. And they're easier to version control because they don't have all the overhead of Excel and all the formatting and that sort of stuff. It's just sort of a way to store raw numbers. So just an example of how to read in a CSV, we'll just write the staff data frame to file, and that's just using this write.csv file. The first parameter you feed in is the name of the data frame, and then you feed in the name of the file you want. You can do something like, you know, have a folder name and it'll go into a folder based on that, but otherwise it just saves into your working directory. So your working directory is where RStudio is currently pointing, and if you look here at the top of your console, that's the folder it's pointing to. You can also figure it out by typing get WIT, which is get working directory, and so that's the path on my computer where the working directory is pointed. Also, the files tab in this pane is the same. It's the view of the working directory, and you can also navigate around in here, but then if you move away from your working directory, you can click this little arrow and it resets that to your working directory. I do that a lot. Anyway, so if I use this write CSV file, you will see the staff CSV appears in my folder there. And then we can read it in by using the read CSV function. We enter in the name of the file, and again, you can put in like a whole path there if you want. But that's not necessary. And we assign it to variable. So a word on strings as factors. So Jason, did you talk about factors? Factors are a sort of special class. If you imagine like a multiple choice question and you can answer A, B, C, or D, but sort of there are only those 4 acceptable answers, that's what a factor really is. It is sometimes essential potentially in building predictive models where you don't want values that don't exist within sort of the 4 things that you want them to be. So older versions of R default by reading in string columns, so such as department or name, it reads them in as factors. Newer versions of R, so anything from 4 onwards, defaults to reading them in as strings. Generally, you're going to need to do some data cleaning, so it's generally best to read in as strings and then make sure everything's the way you want it and then convert to factors, unless you sort of know the exact process by which your data is being generated and you know it's clean. So if I do that with strings as factors set to false, and I do type of, I don't know if this is actually doing it. Department, you'll see that's coming as a character. And if I do it with strings as factors set to true, that should have come in as a factor. I don't know. Let's not worry about that too much. But if you're ever trying to manipulate something you think should be a string and you're getting errors about levels, that's because it's set to a factor. You need to convert it back to a string before you can change it. So there are various ways in which we can look at the different parts of data in our data frame. So head is a really useful function. It just prints the top 6 lines of the data frame. I don't know why it's 6, but it's what it is. You can change that by just entering in a number as a second parameter and it'll print that many lines. Sorry, my dog's just found his squeaky toy. Likewise, there is also the tail, which shows you the bottom rows. STR is for structure of Iris, and it tells you at the start that it's a data frame, that there's 150 observations, so that means rows, and 5 variables, which are the different columns. And then it tells you the detail about each column. You can see that this is a factor and it's got 3 levels. You can only see 2 of them. The first 4 columns are numbers, and then these are the first few rows. You can just sort of see the values there. What this actually means here, so there are 3 levels. There's Setosa, there's versicolor, and there's something else. But these ones all mean that they are Setosa. So it's the first level. And so I think that's probably more memory efficient to store it as a factor rather than a variable, as a character. But that's probably. So summary of Iris is also a really useful way to get to know your data. And it's, I believe Jason showed you the summary fact before. So of a numeric, it'll do, or an integer or a double, it'll do a numeric summary. So we can see we've got the min value, the max value, the quarter values, and the median and the mean of all of those. And then for the factor, it does a count of the different values. So yeah, the data set is 153 of each of these different species. Cool. And finally, plot. We'll talk about data visualization later, but we won't really use the plot function. Plot is a way to very quickly look at things, and it will work on a data frame, and it gives you this lovely view, which is a grid of every variable compared to every other variable. You wouldn't want to do this when you have a huge data set, but it does, like you can see right here that this is the combination of petal width and species, but you can see that petal width is a good way to distinguish the 3 species just already with that quick level of analysis. Cool. So other things you may want to know about a data frame are its shape and size. We describe it as a shape, which is sort of the number of columns, the number of rows. So dim is for dimension, and it just gives you this vector. So that's the number of rows. Everything that happens with data frames, rows comes first and then columns. Or you can do n row, which is the number of rows, or n col, which is the number of columns. For like, there might be sort of some examples where you want to set up a for loop where you go over every column or over every row. And so you do something like for I in 1 through n col. Can you please put yourself on mute, Johnny? So more advanced ways to access elements of the data frame. So names will give you a list of the column names of the data frame. And again, if you're working with large data frames, this is really helpful because you will forget exactly what something's called and when there's underscores versus spaces or stops or whatever. So that's just a vector that you can just access like any other vector as well. So I probably should have found a quiet keyboard for this. So what you can then do is use a $sign to access different columns of the data frame. So iris $ sepal length will extract the sepal length column as a vector. And then you can access elements of that vector the same way you would any other vector. So iris sepal length 1 gives us that first value, 5.1. You can then access by using an index. So 1 means the first row and the next one means the first column, which again gets us 5.1 because it's that first volume, first column. And then you can use all sorts of subsetting like we saw earlier. So 1 through 3 will give us 1, 2, 3, and this will give us a vector of 1 and 5. So we get the first 3 rows and the first column and the fifth column. You can also, so this is putting in a row definition and a column definition. If you leave either one of those blank, it returns everything. So this iris 1 through 2, comma, nothing gives us the first 2 rows and all the columns. And again, these sorts of things are useful when you're getting used to your data, especially with a larger data frame. You might just want to look at little bits at a time or look at relationships between just a few variables rather than everything. So some really helpful functions when dealing with data frames. Table is one that I use a lot as well. It's much better for looking at categorical variables than numeric ones. And it just does account for a character or a factor variable or a logical. It'll just show you a count of every value. So again, 50, 50, 50 as we discussed earlier. You can do it for numeric, but you wind up with something like this. Oh, sorry, as well, you can look at 2 variables at once. And so this is looking at species and petal length. But we see here that this is not very useful because the numeric has such definition that there's too many variables and you can't really see a lot of detail. So instead, we can feed in this, which is a logical function, not function, logical, I can't remember the word right now. But what it will do is it'll compare every value of petal length, see if it's less than or equal to 2, and return true or false. And this is what did I say, petal length. So this is one of those features of the iris that's very different between species. And you can see that right there, that all the Setosta have longer petal lengths and the versicolor, and Virginia have the shorter ones. You can actually feed a third factor into a table like this, and you wind up with, it creates a 2-level table and then creates a single one of those for every variable combination. So it prints out a lot to the screen, but looking at 2 levels, especially sort of summarized, can be very useful. So if we look at, I don't know why exactly I put that head there again, but that's just the structure. So we've got 4 columns of numerics and 1 of a character. So I can't really do maths with the character, but I just wanted to show you the apply function. So apply takes a function and it applies it over 1 dimension of a data frame. So you can apply it to either all the columns or all the rows. And same as when you index the data frame, the number 1 here means do it on every row, and the number 2 means do it on every column. So the apply function takes the data frame first. So I'm feeding in all rows, but just the first 4 columns so that we can see the maths that happens. So 1 or 2 is the axis, that's the actual term, the axis over which we apply it. So the rows or columns, and then sum is the function. So if I do it over all the rows, I wind up with 150 values. That is the sepal length plus the width plus the petal details. And if I do it over all the columns, I wind up with 4 values, which is the sum of all second lengths of flowers. Does anyone have any questions? I see some stuff's popping up in chat. I've just been ranting along. We're all talking about the recording. Okay. Cool. So what we're going to talk about next is updating values in the data frame. So I showed earlier that doing something like this, iris11, gives us access to that first column, first row. We can also use this to assign it a new value. So if I press that, oops, sorry. So if I run that and then we look at head iris again, you'll see the first value has changed to 200. There's also an option called fix iris. So when we press fix iris, we get this lovely pop-up like this, and we can change all the values just by typing them in. Change that. You then just close that. If we look at the head of iris again, we can see that's gone back to 5.1. This has become 3.25, and so on. It is worth noting that that will save it only to this object. So if we quit RStudio, those changes will have been lost. They don't get updated to a CSV or anything like that. So next we talk about missing values. So missing values occur when, we ask for there to be a variable with a value, but that value cannot be calculated. So NA is the not applicable, I guess. And so you can actually see there that that's gone blue. And that's because NA, like it's not a string, it's a special value. And it can be a numeric. Let's call that. NaN means not a number. There will be slight, and again, that's sort of a special value. It's not a string. There are slight differences in NA and NaN that I can't remember off the top of my head. But what's really useful to know about these is there are certain functions that freak out when you feed in NA values. And so, if you're getting a weird error and you don't know what it is, or if the error is very clearly that there are NA values in your vector, then you need to go through and clear them out and do something with them. So an example where they might appear, so one of the main ones which I don't have here is if you have a CSV and you've read it in and there are empty cells in your CSV, they will come in as NA. So if that's a string column, you might want to go through and replace them all with just a blank string, because a blank string, just like this, is different to NA and it is actually a value. If they're numerics, you might want to replace them with zeros or something like that. Another way it can come up is if I create a vector like this. So these are all strings at the moment. And I try to convert that to a numeric. So we're just using the as numeric function and feeding in that X factor. We get this warning message, which is nice. NAs was introduced by coercion. If we look at Y, you'll see that cheese has converted to NA because there is no numeric value for cheese. But the 1 and the 2, it could figure out was a number. So if we then take the mean of Y, we get NA because it doesn't like that NA values. It doesn't really know what to do with it. So a lot of functions will have something like this NARM, which means the RM is removed. So it just means remove all the NAs as you calculate. And so in this instance, the mean is the value 1.5, which is what you get, is the average of 1 and 2, right? So yeah, if you're ever getting NAs, you can look for that sort of parameter to feed into your function. Table is, as I mentioned earlier, if you can give it this use NA equals always, or there's other values there, but you can use it to show a count of the NAs in your data. Summary will also give you a count of NAs, and then there's this lovely function is NA, which just returns a logical true or false, which you can also feed into the function, the table function. So it's always good if stuff's not working to check for NAs in your data. Cool. We're going to jump onto data visualization now. PowerPoint's crashed on me as well. So we're going to be using a library called ggplot2. So plot just means plotting a graph. GG refers to grammar of graphics. And that is, that is sort of something that was defined a long time ago in this, I didn't write it, but there was this guy, his name's Edward Tufte. He was basically considered the founder of sort of modern data visualization. He defined these 7 layers of graphics that would go into how you draw and how you define and display data. And so these 7 layers, we're running out of time, so I'm not really going to go into it, but it's just sort of different shapes and different parts of it. You can read on it later. So the basic scatter graph is we start by using the ggplot function and we feed into it a data set. So this MPG is the data set I showed you. Oh, it's a slightly different data set from earlier. MPG. Okay, might just be empty cars. That's what it is. Okay, so everyone, if you're following along with your code, library ggplot will load the library into your environment, which means you can access all the functions. It also means you can access the data sets in ggplot2, which is actually where MPG comes from. Okay, so we're using this because it's got a lot more categorical variables, so just allow me to show the features a bit more. So we've got displacement, year, cylinders. So the CTY is miles per gallon in the city, and HWY is miles per gallon on the highway, and then everything else is just sort of a description of the car. So that's the data frame we're going to look at. So with ggplot, I think it's similar for Plotly, which is the other major plot, graphical package in R. The sort of main function is this ggplot MP, which we feed in the data set to, but that doesn't actually create a graph. It just sort of creates a graphic space. So what we do instead is you see this plus here, that plus is very important. That plus has to be on the top line to show that something else is coming. If you put it here, it doesn't work. So always make sure that your plus is up there. So we do use the ggplot to start the plot, and then we add our layers. So the first example is geom point. So geom basically means a shape that we use to represent our data, and there's a lot of different functions. So it's geom underscore point will draw this sort of scatter plot, and geom underscore line will draw a line perhaps, but we'll get there in a second. So we start with the ggplot creating an empty coordinate system, and we add layers. And we use this mapping function. AES stands for aesthetics, which sort of comes back to the grammar of graphics thing. And that's how we feed the data into which axis is being used. So the x-axis is going to be displacement and the y-axis is going to be highway. Run that in R. And then that's where we get our graph in the viewer. I just want to add as well, I completely forgot to put in a slide about how we save the graphs out of R. So there's 2 main ways to do it. One is there's an export button here. So you can save it as an image, a PDF, or copy it to clipboard. And you just get this pop-up. You click directory to select a file, and then you can just save it. The other way of doing it is you sort of, when you do something like this, it pumps it to the viewer, but you can use a different function to pump it somewhere else. And so, for example, you could do JPEG and you put in a file name. And that, whatever, we'll use PNG. I know PNG works. So that opens a connection to a PNG file. If I look at the files here, you'll see that it's been created and it's got 0 bytes because there's nothing in it yet. So yeah, it sets up that way of doing it. We then run the graph function and you'll see it hasn't appeared in the viewer. And then we use the function dev, which stands for device.off. And you see now there's 3.3 kilobytes in the file. So that dev.off is really important to close the file. And it means that you can actually open the file once you get to your directory. File name, there it is. I will update the slides and get a new version sent out to you with that information in it. Anyway, let's talk about different graphing options. So as I said, there's a geom point function. There's also a geom line function. You'll notice I've subsetted the data to just ALDIs for this because it just makes it a bit clearer to see. Cool. And then we've got that nice line instead. You can also add these layers together. And so we draw that same line, but we add points as well. And that's how you get the dots on the chart if you want a sort of slightly different version of the display. We also can do different things to the plot and we can add extra data by doing so. So in this one, you notice it's an American spelling of colour. I don't know quite what it is because a New Zealander wrote it, but whatever. And so by adding the class, which is compact versus sedan versus whatever, we can add more information to the same chart. And it's sort of defaulted to these colours, which wasn't noticed the other day, but that's fine. And it generates the legend automatically. So you can see we've now got 3 variables on that chart. Other ways you can do it is by size. And so size is, we make the dots smaller or bigger, and that's a good way to demonstrate numeric data. I don't know why this is drawing so slowly, but you can see here, sort of you've got a max of 35, and that's the big dot, and this tiny dot means 10. Alpha is the term used to define the transparency of each geom. And again, it is numeric, and you can see these light coloured dots. So alpha is really good for helping display multiple sets of data. So what's happening here is, oh no, that's not what I'm doing that, sorry. So a low alpha means it's transparent, so it looks pale and grey, and so those are our 10s and our 35s. Our other option is shape. I've gone back to class here. This is a bit of a problem because ggplot defaults to having only 7 shapes. Oh no, 6 shapes, and I have 7, so SUV is not plotted at all. There are, if you Google it, you will find there are like 20 different shapes available. So there's like squares, and there's like square borders and circle borders and different types of stars and whatever. So you can look into that, but you can see I've got circles and triangles and stars and stuff there. What I don't have the code for, but hopefully is on the deck, is you can also use all of these all together. And so you can see I've got year as the size of the thing. I've got color defining the brand. I've got class based on shape. And so this is a great way to express a lot of information all at once, but it's always a good question to ask in data visualization. Am I adding extra value by doing this? A very smart and renowned data scientist said to me once that the road to hell is paved with sexy visualizations because people try to make it fancy. And Edward Tufte, who I mentioned before, this is the name of the book he wrote that revolutionized data visualization. And he sort of defined key areas and key ways to make your charts clear and sensible. And he describes this graph here as one of the worst pieces of data visualization ever published, because you can see it's actually only got like 8 data points on it, but there's this huge complex thing going on that doesn't make any sense. Again, if you've got some time and you're interested, I'd really recommend Googling this, but I won't go through it in detail now. What he is a big fan of, though, is small multiples, which we can talk about. So rather than having this one chart that has all the shit on it, we break them up into smaller versions of the chart, and facets are how we do that. So this is an example where we have 3 bits of information, so displacement, highway, and class, and we use facet wrap, which means it's split class up into different charts. So the two-seater has this relationship between highway and displacement. And this is actually a clearer way to express that same information. So Edward Tufte would prefer this graph over that highly coloured abomination I showed you earlier. Facet grid is a similar sort of thing, but it draws a grid of charts based on the DRV and SIL variables, and it plots displacement and highway on each of those charts. And it's really slow. And so you can see there's, this combination doesn't exist, so this chart is blank, but you can sort of see if there was a good relationship between sort of this and this, was the relationship between 2 variables was changing according to the 3rd variable, this is exactly how you show that. Cool, so some other important ones, histogram. A histogram works based on numeric variables, and it automatically calculates bins for you according to some algorithm. Some versions of histogram, you can actually define which algorithm you want to use to shape your bins or not. Or you can use these features. Bin width means this is the value of X. I want to be 1 for each bin. So you can see here we've got from like 2 to or 1.5 to 8. If I set bin width to 1, I get a bin for like 1 to 2, a bin for 2 to 3, and so on. Or you can set a number of bins if that's what you want to do. And so there'll be 10 different bins here, and the numbers will be split, and they'll be evenly sized bins according to the x-axis. So if you want to draw sort of a histogram of a categorical variable, you use G on bar, that gets a bar chart. And so you can see we've got just 20 Audis, we've got a lot more Dodges, and so on. And then we can also add more information to that with more aesthetics by changing the fill so that the color is telling us what the transmission is. And so that is what in Excel you'd called a stacked bar chart. We can do a groups bar chart by using this position variable. No, that's going to make the 100% stacked chart. So I want to talk about, Jeep, because Jeep has a lot more cars than Audi, but you want to compare what percentage of each car is a auto L5, then you'd use this chart. And then if you want to look at sort of the other main way to do a bar chart is a grouped bar chart. So you use position equals Dodge for that, and you get this chart. And so that's a different way to show the same numbers, and they tell different stories, and that's what you need to think about visualization, what story does it tell. I also was going to do a whole thing in which we talked about color themes, and you can see that this is a lot prettier than that mess using Scalefill Brewer. Again, we're running out of time. I don't know, I'm just going to draw. Oh, and I'm not sure, sorry. I'm sure I had a point for drawing in that chart. Oh, I think it was just about. So another quick word as well, rainbows kill people. That's a scientific fact. There was a study in which they gave doctors x-rays, but they coloured it according to the rainbow as opposed to just a grayscale, like black is thick and white is not. And those doctors being shown rainbow x-rays made a lot worse decisions. And so colour can convey information, but it can also really screw things up. There was this very smart woman called Brewer, and she created a whole bunch of spectrums that are really good and really accessible in R for displaying your data. So there's 3 basic ways of doing it. This is just a pale to dark. Oh, you can see it's actually changing colors as it's doing it. And so that you convey information about there is a small percentage of disease in this area compared to a high percentage of disease in this area. There are these categorical things. So, you know, green would mean an electrician, whereas purple would mean a dentist or something like that. And so this is the only situation in which using rainbows is really safe, because you're not trying to compare hue as a numeric value. And finally, we have these double spectrums. And so these are really great when you want to show deviation from a mean. And so you might want to, so sort of average is a very pale color. And then if something is really high above average, like you're earning way more money, like the, you know, sort of average income is way higher in a certain area, you go one color, and if it's way lower, you show a different color. And so you sort of show direction and magnitude in the same chart. Resources for data visualization, I'll be very, very quick. These are some great websites. So the person who built the ggplot package in R has made all of it available for free. This website, we will be sending the slides out later. So I saw someone asking that, so you can look at this then. This is where you can access the whole book for free, and GitHub is where you can access all the code examples in the thing for free. RStudio cheat sheets are a great resource. So they're all free. People can enter them as they wish. So there's one specifically on ggplot, and it's just got all the different functions, all the different things you might want to try and do with it. But it's also got all sorts of different functions on string manipulation, on various other packages. It's a great resource. I'd really check it out. This is what the ggplot one looks like. And so it's sort of, you can see that's a line graph, that's a smooth geom. This is a website made by that brewer woman, Cynthia was her name, and it helps you pick color schemes, either qualitative, diverging, sequential, and sort of it gives you all the hex values. You can just copy them into whatever you're using to draw your chart. This is a really fun website. This is where people who have created their own extensions of ggplot to show their own very unique visualizations. This is where you can access all of those. You can see some really cool stuff that's been drawn in ggplot in R. Oh, I was actually helping a friend with this function today. That's awesome. And then the other thing for all of R and all of computer programming and all of statistics is Stack Overflow. When you Google the question on R, like how do I apply a function to each column of the data frame, you can see the second answer here is Stack Overflow. It is a message board, it's free to use, but the people on there know their stuff, and you know, you can upvote answers, but sort of any problem you have, if you can describe it, Google that, and if there's a Stack Overflow answer, click on it. If it's an error, copy the error into your Google search, just search for it and you'll generally get an answer. But Stack Overflow is an amazing resource. Oh, and that slide's in there twice for someone. All right, that's all I had. Thank you.
Awesome. Thank you so much, Jude. Amazing second half of the presentation there, and some really useful resources that I'm sure students will want to dive into. So just reiterating what's been mentioned in the chat, we'll be sending through the recording as well as the solutions to the worksheet that we've been working through today, and the slides as well, following up on an email after the workshop. And I'll just pass on to Sue to conclude.
Yeah, so thank you everyone for attending WIT and Quantium coding workshop. And special thanks to our representatives from Quantium, Jude and Jason, for co-hosting this workshop and sharing with us your knowledge and insights in R. We hope that this gives everyone an opportunity to get an understanding of R and the application of R in workplace. Also, our WIT team strive to produce high quality events, so we greatly appreciate any feedback from today's event. Please fill out our feedback form linked in the Zoom chat, or you can also scan the QR code on the screen. So if you enjoyed today's workshop and would like to attend more, we are having multiple events coming up. Firstly is a tableau workshop with Mark Nicole this Thursday. where you can learn how to develop your data visualization and analytical skills using Tableau software. Secondly, we also have imposter syndrome with Eucalyptus next Thursday, where you will acquire some tips and tricks to help you overcome imposter syndrome and learn how to confidently promote yourself within workplace. And we also have InterVarsity Diversity Tech Panel in week 4, where you get to hear from a range of industry professionals about their experiences in the tech industry and get to meet people from other universities. So if you're interested, make sure you check out our Facebook page and register. Thank you everyone again for joining us tonight, and have a good evening.